Welcome to the deep dive. Today, we're heading way up, literally, to explore a really surprising atmospheric event.
Yeah.
Happened during that powerful solar storm back on Mother's Day.
Right. And our mission today really is to get our heads around this unexpected activity. It's in a part of Earth's atmosphere that, well, usually doesn't get much attention during these kinds of things.
Yeah, and figure out what it all means.
Exactly. What are the implications?
We've got some fascinating findings here, just published in Geophysical Research Letters. Comes from scientists at Kyushu University.
And they use data from quite a network, 37 ground-based radars, ionosones, they're called.
Ionosones, right. And also data from the Cosmic 2 satellite network.
So you've got eyes on the sky from below and above. Pretty comprehensive.
It really is. And what's so interesting, is that usually when a big storm hits, the focus is way higher up.
Yeah, the F layer of the ionosphere, typically, much higher.
But this study, they looked lower down, the sporadic E layer.
That's the one. It sits roughly between 90 and 120 kilometers up. And yeah, what they found there was, well, it wasn't expected.
Okay, so this sporadic E layer, let's unpack that a bit. What exactly are we talking about?
Well, the ionosphere generally, it's where atmospheric gases get ionized by solar and cosmic radiation, electrically charged.
Right.
The sporadic E layer is kind of special within that. You get these really thin layers, maybe only 1 to 5 kilometers thick.
Very thin.
Yeah, but they're packed, really dense with ionized metal particles. They call them sporadic E clouds.
Sporadic E cloud.
And they're fleeting. They can pop up, disappear pretty suddenly, like these little concentrated patches of charged metal just hanging out.
Sporadic makes sense then.
Yeah.
So why the lack of focus during solar storms before now? If they're dense, wouldn't they react?
Well, the general assumption, kind of the prevailing thought, was that they weren't really significantly affected.
Okay.
The F layer you see, it's much more heavily ionized all the time, so it was always seen as the main player, where the storm's energy really made a difference. The E layer was sort of background noise during these events.
A bit overlooked.
Definitely overlooked.
But then came the Mother's Day storm. That was a big one, wasn't it?
Oh, yeah. A really major geomagnetic storm, basically a huge disturbance of Earth's magnetic field caused by, a massive dump of energy from the solar wind.
And the Kyushu team found something different this time.
They did. They saw this unusual increase in the intensity of those sporadic E clouds. But here's the kicker.
Yeah.
It wasn't most noticeable during the storm's peak intensity. It was afterwards, during the recovery phase.
Really?
Okay?
After the main event had passed. That is surprising.
Mm-hmm.
And this wasn't just in one spot, was it? Where did they see this?
No, it was quite widespread geographically. They found it concentrated over Southeast Asia, Australia, the South Pacific, and the East Pacific.
Wow, it's a huge area.
A very significant chunk of the globe saw this unusual E-layer activity.
But there's more to it, right? Something about movement.
Yes. This was maybe the most surprising bit. The clouds weren't just getting stronger, they seemed to be, moving.
Moving? How?
The data showed what looked like a clear progression, a movement of these sporadic E clouds starting from the polar regions.
Both poles, Arctic and Antarctic.
Earth poles, yeah. Moving over time towards the equator, like they were being swept across the planet.
Swept across the planet. That's wild. Do they have an idea why?
They have a leading hypothesis, yes. They think it's down to large-scale atmospheric waves.
Waves in the atmosphere.
Triggered by the solar storm's initial impact higher up. The idea is these waves disturbed the neutral winds in that E region.
Okay, neutral winds. So not the charged particles, but the regular air movement.
Exactly. The atmosphere has both charged ions and neutral atoms and molecules. Winds move the neutral stuff. The storm's energy creates these big disturbances, these ripples, that travel downwards and sideways. Professor Huixin Liu, who led the study, pointed specifically to these disturbed neutral winds pushing the ionized clouds around.
Makes sense, like ripples on a pond, but huge atmospheric ones.
Sort of, yeah. That's a decent analogy.
Tracking that kind of thing globally must have needed incredible data. You mentioned the ionosondes and satellites.
Absolutely. The combination was key. Those 37 ionosondes pinging the ionosphere from the ground, listening for the echoes.
Gives you the details locally.
Exactly. Density, height. Then you add the Cosmic 2 satellites, which give you that global perspective, measuring how GPS signals bend as they pass through the atmosphere.
Okay. Different techniques, same goal.
Right. Putting them together gave this incredibly detailed map of sporadic E activity, not just at the peak, but crucially during that recovery phase, too. That's how they spotted the intensification and movement.
So this is more than just, fascinating atmospheric science. It has real-world consequences, doesn't it? Why should we care about these clouds moving around?
Oh, definitely. That sporadic E layer, even being thin, can really mess with radio communications,
Which kinds?
particularly in the HF high frequency and VHF very high frequency bands.
Okay. What uses those?
Well, quite a lot. Think amateur radio operators, some long-distance broadcasting, certain aviation communication systems, even some military comms rely on those frequencies bouncing off the ionosphere.
Right. So if these dense clouds suddenly appear or intensify where you don't expect them,
They can block the signals, scatter them, or even reflect them in weird ways, causing interference or complete blackouts. It's unpredictable.
so understanding this better could actually help predict, maybe even prevent, those kinds of communication disruptions.
That's the goal. That's the hope, absolutely. The researchers think that by understanding how these layers react after the storm, especially this pole-to-equator movement,
You get a warning sign.
potentially, yes, you might be able to improve forecasting. If you can predict, okay, based on this storm's characteristics, we expect intense sporadic E to develop over this region in the next, say, 12 hours, then maybe you can mitigate the impact.
Reroute communications, perhaps,
Yeah.
or just be aware of potential issues.
Exactly. Professor Liu mentions specifically using these propagation characteristics they observed to maybe predict sporadic E more accurately in the future.
That sounds incredibly useful.
And-
Are they stopping with just this one storm, or are they looking further?
Oh no, they're planning to dig deeper. The team wants to go back and look at data from other big solar storms.
To see if it's a pattern?
Precisely.
Yep.
Was this Mother's Day event unique, or does this E-layer intensification and movement happen regularly during the recovery phase? That comparison is crucial.
Build a bigger picture.
Yeah, it helps build a much more robust understanding of the whole process.
It's just amazing, isn't it, how this research brings a whole new focus to a part of the atmosphere we sort of ignored during these events.
It really is. It underlines how interconnected everything is, space weather hitting us way out in the magnetosphere, and the effects rippling down even to these lower, less ionized layers.
We always hear about the F layer, 150 to 500 kilometers up, taking the main hit.
And it does, but this shows the E-layer isn't just passively sitting there. It has its own dynamic response, and it's geographically huge. A good reminder, there's still plenty to learn up there.
Okay, so let's just quickly recap. This deep dive showed that the Mother's Day solar storm triggered some really unexpected action in the sporadic E layer.
A big increase in density, specifically during the storm's recovery.
And these dense clouds of ionized metal seem to migrate, moving from the poles down towards the equator.
Likely pushed by atmospheric waves and disturbed neutral winds set off by the storm itself.
And this is important for us because these layers can play havoc with HF and VHF radio signals.
Exactly. So understanding this could lead to much better forecasting of these kinds of communication disruptions.
Which is definitely a positive step.
It really opens up a new angle for space weather research, looking at these less studied regions.
Which leaves us with a final thought, doesn't it? If a major solar storm can cause such surprising widespread effects in this lower part of the ionosphere, this area we previously overlooked, well, what other hidden connections are there? What other atmospheric phenomena might be reacting to space weather or other events in ways that could impact our technology or environment, ways we just haven't figured out yet?
Makes you wonder what else is going on right above our heads.
It certainly does. Thanks for taking that deep dive with us.